so these lectures are recorded, by the way, and we convert them to YouTube videos and give you guys the links to the YouTube videos. All right, so, darn it, I forgot my microphone. It still picks up my voice, but not as clearly as I'd like. So anyway, I guess one question, our digital flagship university status. Does everyone here have an iPad? I don't need to bring handouts to the class anymore, right? No, it doesn't look that way, does it? All right, so we're not there yet. They've been promising that. It doesn't seem to be coming into effect. Is that the year after you guys, or right? 2 years after you guys? Oh God, keep cutting trees for another 2 years. All right. It's just one of those things that we were promised. So we're here to foster an understanding of structure-property relationships, as the course is described, and to survey the broad field of polymer science and engineering, introduce the student to important concepts that distinguish plastics from inorganic materials. And at least for the first half of the semester, I'll be talking about bonding in polymers, polymer architecture and microstructure, trying to make connections to what you guys already know about inorganic microstructure, and there are some connections. There are some easy misconceptions to develop as well, so we need to be careful you don't fall into that trap. We do talk about crystallization and thermal analysis, both of which are very helpful in terms of understanding polymer behavior and properties. And we do talk about recycling and the big six. And so there are thousands, tens of thousands, maybe hundreds of thousands of polymer structures out there. People have been making polymers for a very long time. Trying to come up with the next Kevlar, for example, is a big push. And so people are constantly synthesizing new polymer structures. But I'm only going to force you to memorize 6, maybe 7, if I get to it, polymer structures. And you'll need to know what those are. And you need to write them down, spell their names correctly. You guys might want syllabi, I'm guessing. Oh, sure. Anybody else need a piece of my fan? No? Okay. And mechanical properties and additives, and this is something else we learned a lot about, plastics. We talk about them as a class of materials as if they're some kind of homogeneous structure, but in reality they're rarely ever homogeneous. So that is red, all right? There's no such thing as red polymer out there, all right? So all plastics that you see and you experience are largely containing additives of some kind or another. And originally those were added for mechanical purposes to make plastics stronger, but now we make them red and shiny gold colors and various things. So aesthetics is a huge driving force for plastics and their adoption. And then we do talk a little bit about some issues involving manufacturing and unit ops, and case studies of fracture, if we can get to it, as well as diffusion. And the class grades are based on a small amount of quizzes and homework. And so I give what are called concept tests, which are kind of quizzes, except I give you the right answer at the end of the section. So they're not exactly quizzes, but I do give those to try to get you to understand some of these more abstract concepts associated with plastics. And there are a lot of them, so it's a good tool. We'll have 3 exams and 1 final that constitute the remaining portion of the class. Any questions about that so far? That will make sense? All right. Okay, this is not an organic chemistry class, which usually causes some people to breathe a sigh of relief. It could be, if you want it to. There's lots of organic chemistry to talk about when it comes to polymers, but I don't spend much time focusing on that. We'll get into a little bit about some reactions for the second half of the semester, but not that much. And as I said earlier, you're only responsible for a limited number of polymeric structures, understanding how to spell their names and various things like that. Relatively simple chemical reactions. We do have some abstract concepts, entropy being one of them. Again, you guys aren't used to thinking about entropy and what it means and how it is important in the context of these particular materials. Plastic properties and product design, and then, as I said earlier, I try to pull in things you are familiar with. So crystallization is one of those things that I spend a lot of time talking about because we're used to thinking about those types of structures, and it is important to us in terms of controlling the properties of various types of plastics. Okay, so I'll go ahead and do my federally obligated duty here and take roll. So I'll start with a really long one. Let's see. Tim Allen. Okay. Ben Adreski. Okay. Michael Andy. Okay. Tony Anarino. Okay. I should know how to say that. Joshua Argo. Okay. Victoria Black. Dominic Bolin. Ignatius Brossart. Moline Sao. Hi Chen, you're here. All right. Matthew Kolichis, 8. Juelong Dai. Anna Debsky. All right. Arjun Dinan. Arjun? Is that close?
Arjun, Dinan.
Dinan? Okay. All right. Travis Bell. Daniel Estelle. Nitin Gopinath. Sophie Hess. Okay. Connor Holliday. Morgan Highland. Carl Jacobson. Thank you. Doug Gayuha. Thank you. Justin Krantz. Emily Lapoya. Is that close? All right. Talalupe Lawal. That's probably nowhere near close, is it? Tolu? Okay, all right. That's a lot easier. Broderick Lewis. Khalid Mohammed. Marina Nido. Marcus Nogaj. Is that far off? No J? Really? Okay. That's way off. All right. Aaron Pennick, I'm sorry. Kavya Raguraman. Emma Schmitz. Connor Varney. Jeffrey Vijay. Okay, thank you. Anila is here. Nick Wallace. Allison Whitney. All right. Matt Weedo. And Sivan Zoella. Sivan. S-I-V-A-N. Not here? All right. And then on to the graduate students. Ji Chen. Ooh. Flint Colvin. Thank you. Summer Galentine. Daniel Humrick. Okay. Mitch Kahn. All the graduate students are sitting in the front. What does that mean? Medya Kasula. Continuing the trend. And Faiz Khan. Ah, you broke the trend. And Bonnie's sitting right here, so she's keeping with the trend. All right. Wow. So only one person missing out of all that. Okay. Any other questions so far? Concerns, etc.? Nothing? All right. So this is an introductory lecture, and so I'll give you a little bit of history. I'll stand up here and sweat. And then go into some definitions and some structural tricks that we play to assist us in actually learning about these issues. So polymers in recent history, as far as ancient history is concerned, there was a need to control water, and that was what drove a lot of early interest in various things that aren't exactly plastics, but were polymeric, and trying to use those in interesting ways to control water. And that led in the 1800s to lots of interfaces with some of the technologies that were coming online at that point in history. One of the early ones is phonograph records or cylinders that were made of wax. And so this is how we initially started recording sound. And this was certainly important to us at earlier ages. And then one of the other applications in which we were looking at trying to come up with new materials involved ivory. And as a manufacturing process, this is a really crazy idea. You go over to Africa, you kill a bunch of elephants, you ship their trunks to the United States, and then you carve them into these various shapes. It doesn't sound like a very efficient way of making things. All right, but that was used and for a long time, piano keys, knife handles, combs, and billiard balls. And so this gives you an idea of how desperate they were. That they had to go to an entirely different country, kill these large animals, and then ship their tusks over here because they couldn't find anything in the horizon that met the needs. So wood, metal, ceramics, just too difficult to make a comb out of. All right. You can imagine carving a comb out of wood. So it was more practical, unbelievably, to do things with elephant tusks rather than try to come up with some of the material. And one of the interesting stories is a material called gutta percha, which is derived from the sap of gutta percha trees in Borneo, discovered in the 1600s. And again, something that people found very useful, kind of like rubber plant, a different type of material, actually different color. And this, unbelievably, to me at least, this was actually used as cable insulation until the 1940s, well into the birth of plastics, modern plastics. So this tells you how desperate they were to try to come up with something that could insulate electricity. So they had to go to Borneo and cut down some trees and come up with the raw materials for that, using that. Crazy ideas that were necessary because we had nothing else that could do the same job. And so the word rubber came to us from Joseph Priestley, who found out that this could be used as an eraser. And so rubber in this context means the rubber plant, which is not as far away as Borneo, only in South America. And so this is the birth of rubber, as we call it, but it largely involved just something that was derived from the plant. And so replacing using the sap from this plant, concentrating it, and trying to use it as a material. But we didn't get around to what we truly think of as rubber until Charles Goodyear, who was actually trying to sell valves for life preservers, which it's a pretty important thing back in the day, came across the problem that the rubber they were using for the life preservers melted when it got hot during the summer. And so that gives you an idea of one of the limitations of the early rubber derived from these plants, in that it wasn't very good, it wasn't very strong in the presence of even mildly warm temperatures. And so what Goodyear did, he stopped trying to sell valves because it didn't make sense to sell valves for something that melted when the summer hit. And started trying to convert rubber into something useful by mixing it with various dry powders. And this was very serendipitous, just a matter of mixing together. And he did this for a couple of years. He actually went to jail. He was in debtor's prison for a little while because of the fact that he was not doing a very good job of manufacturing his life preserver business. But anyway, he did a lot of experiments and made various things. So probably wood flour and sawdust and various things. But again, they didn't resist the summer heat. But then, by accident, very fortunate accident, he added sulfur. And you can imagine there wasn't a lot of sulfur before the mid-1800s anyway. And then, by a doubly good accident, this was placed on a little hot stove where it became what he was looking for, something that didn't sag when it got hot. And so he realized he could then alter this formula and make a lot of different products. And this was the first and by far the most versatile of the modern plastics of that time. All right, so you take rubber and sulfur, heat them, and it becomes more elastic, less soluble, and much less heat sensitive, which is kind of a theme even now for plastics. We worry about these same aspects of plastics and whether they can resist the environment in the right way. And so this immediately became useful in some very technologically oriented areas. Battery separators, again, brand new technology, telephone receivers, frames for photographic plates, cigarette holders, dental materials, and then eventually tires. So they didn't start cranking out tires in the 1850s because they didn't need tires back then. They were still working with wood, essentially. But when the automotive revolution came around, this material was ready for it. And so one of the interesting things is that there's an early rubber that we still work with today in a relatively minor context. If you take a small amount of sulfur, you can make rubber weatherproof. If you take a larger amount of sulfur, you can make it a hard solid. And so a different Goodyear, Nelson, achieved a patent on this, and this was the first truly synthetic hard plastic. So rubber, as you know, is kind of a soft, squishy thing, but this could be made in something that actually resisted a fair amount of stress. And it's still used today in bowling balls. All right, that's those ugly black bowling balls in the alley that aren't the pretty pink ones. All right, those are made from ebonite, the same sulfur plus rubber reaction that caused this whole area to begin with. Electric outlets, combs, fountain pens, saxophone and clarinet mouthpieces, anti-corrosive tank coatings. We still use this, and so it just shows you that something's stayed a long time once they've been discovered. And then, independent of all of that, but also on a technological intersection, was what's called Parkinson, and this was discovered by a photographer, Alexander Parks, who looked at this residue that was left behind when he was developing pictures. This solvent evaporated and became a hard solid, and he said, I wonder if this is useful. And they got several patents on this, and later on he had a business partner, Dentist Phil, patented xylanide, a more stable improvement on Parkinson, and founded a company, etc., and they made chess pieces, etc. And so this again was meeting a need. All right, so rubber met some of the need, but it didn't meet all of the need. And so they're interested in this particular material for the same type of combs and beauty products and so forth, as a means of doing something that was cheaper to make and easier to come by than I. And this very slow loading slide shows you that if you go to eBay, you can buy this stuff. Victorian Parkinson plastic brooch. I don't know when it was made, but obviously it's relatively old. Not very expensive in the scheme of things. And that's because it was the plastic of the day. All right, they made a ton of it. And so over here you see art, a vanity set, a dresser made out of this celluloid, which is basically the same material. All sorts of things that look like ivory, but in fact are made of this plastic of the day, the cheap plastic material. So you can buy this stuff on eBay if you want to. So it's out there, and gives you an idea of just how quickly it caught on, because so much of it was made in such a short period of time, because it replaced ivory, which was really hard to get and very expensive. And so this became a very popular manufacturing route very quickly. All right, and so this particular branch of the technology led to the first truly kind of sort of synthetic route to new polymers. All right, so we had this material, this Parkinson material, and one of the things that they found out about it was that you could make something called gun cotton from it. And gun cotton involves not necessarily just guns, but primarily cannon. So back in the early to mid 1800s, they made cannons, and as you guys all know, if you've watched Roadrunner cartoons, which are still very popular, right? I can't imagine, it's amazing how old those things are, and everyone still watches them. Who did not watch Roadrunner cartoons as a kid? All right, still relevant. All right, so as you guys know, you start out with a ball, and then behind that ball, you put gunpowder, right? And then Wile E. Coyote has a fuse, and he lights that fuse. And the idea is all that gunpowder turns into gas very quickly, and that increase in pressure drives the ball out of the cannon and usually misses the roadrunner. All right, and so the issue was that back in the mid-1800s, they weren't very good at machining these large chunks of metal. All right, and so in some cases that ball, if it just had gunpowder behind it, would just kind of fall out the edge of the cannon. And this was especially unpopular when they started putting explosives into the cannonballs themselves. And so what was a solution to this was to use something called gun cotton. And gun cotton, and if you've watched any of those Civil War reenactments, they still use this. You take gun cotton and you put it on top of the gunpowder. And what that does is it makes it seal. So we usually have a crackly machine cannon that still seals that area and allows that gas to expand into a higher pressure ball of gas more quickly, more likely to drive that ball out of the cannon where you'd like it to go. And the nice thing about it, this gun cotton especially, is that it also burns. It has 6 times the gas generation of black powder. All right, so this makes it useful. So you put the gun cotton in and only smoke comes out. Because we're wondering what happened to the gun cotton. Gun cotton also burns. And this is produced by a relatively simple reaction. We have cellulose plus nitric acid. Those two things together under temperature and pressure give you carbon linked to NO2. Whoops. Put sweat on my iPad, sorry. All right, doesn't write very well. And NO2 provides its own oxygen for the reaction, which is why this material burns. All right, you use the same thing in cars today to make them go much faster. And so this nitration process is actually relatively easy to do. I've thought about doing it for purposes of demonstration, but the stuff's kind of unstable. And I don't always get classrooms with windows, so it would be bad if things blew up and there were window for the gas to leave. So anyway, it's something that can be done pretty easily. One of these days I'll do it. All right. What was a readily available source of cellulose in the 1840s? You guys took history, American history, some of you at least. What? Trees. A little more available than that.
Corn.
Cork?
Corn.
Cord.
Corn.
Corn. Oh, closer. What was the war fought of? The Civil War. What?
Cotton.
Cotton. All right. So they took cotton and they made gun cotton out of it. And this military, they made a lot of it. All right. They had warehouses full of the stuff. All right. And some very unhappy people standing in front of mounds of gun cotton was part of that process. And so we had a war. They made just mountains of this stuff, and they put it into warehouses. And one of the problems with this is that gun cotton burns. It burns really easily, and so these warehouses would occasionally explode, sometimes with the people in them, because the gun cotton was easily ignited. All right, and so they didn't have no smoking signs back then, and so things like that would happen. And so what triggered the next stage of development was this need to get rid of all this gun cotton. And they had a $10,000 prize offered up whoever came with a replacement for Ivy billiard balls. And so this fellow, John Wesley Hyatt, can't speak, created the winner of this contest by compression of this nitrocellulose, the stuff that burns very easily, plus camphor. And this created what's called the first thermoplastic, which is celluloid. And celluloid is a very historically important material. And what you're doing is you're taking this relatively easily burned nitrocellulose, mixing it with camphor, which is a powder derived from another natural source. And the camphor acts as a plasticizer. So this is a word you'll see later on, and it's another example of things that we have to add to plastics because otherwise they'd be too brittle. All right, this was part of the early learning curve for the polymers industry in general, was figuring out how to make plastics not break, which sounds kind of crazy. You guys are used to plastics that don't break, but initially that was a problem. And so he took his invention and created what are called Hyatt balls, which were extremely flammable, and portions of the outer shell could explode upon impact. And so they had a saloon owner in Colorado who said that when they broke the rack and the ball would explode, everybody in the saloon would pull their gun because they thought a gunshot had gone off. They fixed that later by mixing in other stuff that didn't burn so easily into it, so they got rid of that problem. And again, you can buy these things on eBay if you want. That's an example of a Hyatt ball that is for sale. So we had these natural materials that could be modified in a variety of ways, and you just saw on eBay some examples of jewelry boxes, hair accessories, items normally made from these very difficult to get materials from the natural world, and a whole bunch of things were made this way. And then film was also made from celluloid, right? And so this is again another intersection with technology. 100 years before this time, we didn't need film. We didn't have photography. But film came about, and we needed to record movies, and this turned out to be the perfect carrier for the photographic materials that allowed us to create film in the first place. This was also very unfortunate because celluloid, certainly that version of it, the early versions still could catch on fire. And so we lost a lot of early movies to the fact that they were made from celluloid and they were sitting around in a warehouse in Hollywood and they burned up spontaneously or intentionally or what have you. So that unfortunately we lost a lot of early films because of the fact that they were made on celluloid. But it was there at the right time, the right place, and was used in the right way. So items made of celluloid are increasingly rare, although you can still buy them. Part of this is driven by the fact that they are unstable. It's still in use for guitar picks, decorative borders, inlays on Indian sitars, and table tennis balls. And if you go to this YouTube link, you can get an idea of just how flammable celluloid is. Because there's I think this is the one where they have 5,238 ping pong balls. They light on fire all at once. It looks like a jet engine going off. It's a very impressive pyrophoric display. Okay, so now we get beyond a lot of this. And one of the reasons why we get beyond it is because chemists start believing in polymers. And so before a certain time period, like 1915 or something like that, in spite of all the evidence that was in front of them, they didn't believe in polymeric structures. They didn't think that a chain could get that long. It would somehow become three-dimensional. It wouldn't remain a polymer. And so they basically thought you belonged in the loony bin if you believed in polymers at all. All right, so it shows you how resistant they were to these new ideas. But once that became accepted and some of the chemistry was worked out, we had this explosion of different materials: polystyrene, PVC, polyethylene, polymethyl methacrylate, nylon as well, all in roughly the same time period. I should point out that it wasn't always easy, like PVC, for example. So Ostromyslinsky made this in 1927, but he made it in an isolated lab in Russia somewhere, and it had a tendency to explode during the reaction process. So they made it in 1927. They couldn't commercialize it for another 20 years because it was so difficult to make. So, but it was made, it was formed. And one example that showed you how quickly things were going, Carruthers he developed the nylon in the confines of the DuPont laboratories in 1937, and he then became obsessed. He failed as a scientist and so forth and so on, and he eventually killed himself right after receiving the patent. And then DuPont itself sold 64 million pairs of nylon in the first year that it became available. So 3 years after he killed himself, this huge moneymaker for DuPont came about. So it's interesting how your perspectives can become a little bit screwed. So one too many. 1938, Teflon was discovered, and it's an interesting story. It's amazing what this guy did. He was attempting to make a new chlorofluorocarbon refrigerant. So this, again, intersection with technology. We just came up with air conditioning. What can we use as a gas to move heat around in air conditioning? And so they were doing this at DuPont, and he had this tetrafluoroethylene gas, and somehow he knew that it had been loaded with tetrafluoroethylene, and he opened it up and nothing came out. Now, I just throw it away and say, okay, next. But he took a saw, a chop saw, and opened the darn cylinder by cutting it. And on the inside, he found out that it had this waxy white material that was extremely slippery. And so that's Teflon as we know today. By 1948, they were producing over 2 million pounds of this stuff in Parkersburg, West Virginia. Who knows about C8, Gen X, PFOA, the environmental pollution that is left behind in the area? You guys heard about this? Pretty nasty stuff. So C8 was used in making Teflon back then, and C8 is now in all the wells, all the rivers. We all carry some small amount of C8 inside of us because it doesn't break down very easily. Right? So there's a lot of concerns in that local area about what it's doing to kidney cancer rates primarily. Polypropylene was made in 1954, polycarbonate in 1957, and in 1938, all these things became very important very quickly. All right, so that's the history portion. Any questions about all that so far? Okay, so we'll get into some terminology, and this is partly driven by the field itself, but also partly driven by the need to draw cartoons and draw various sketches to get points across during this class. And so we have two ways of representing a polymer chain. And one way is to use spaghetti. So we just draw polymer chains going every which way. And I will do this throughout the course of the semester. It's a shorthand way of saying, look, here's a polymer. Look, it's squiggly polymer chains. And this is just, again, shorthand. But it's also polymer chains from 30,000 feet, essentially. So if we instead zoom in on this stuff, you can see that even though at 30,000 feet it looks squiggly, it in fact follows certain rules. So this is sp3 carbon bonding. What is the bond angle of sp3? Point what? 5. Thank you. All right. So we have a certain angle to these, and that angle is 109.5 degrees. All right. So there is some order. You know, we zoom way out, it looks like spaghetti, but we zoom in, and there is actually order to this process. These bond angles aren't random. You go above or below that, eventually that bond breaks. right? And so, but we have two different ways of drawing it, both of which are important in terms of understanding how polymers behave, especially their physical properties. All right, hopefully that makes sense. And then we think about what goes into the system. We have various types of monomers, blah. This is ethylene, which is a gas. And under the right conditions of temperature, pressure, and especially a catalyst, this of course becomes, bless you, we'll see how that turns out. Okay, so this is the name. It says at the bottom here, chain equals macromolecule. You'll see these terms, we use them interchangeably, macromolecules, chains, spaghetti. We think of all these things in the same way. And a lot of what we work with in polymers is amorphous, and that is largely by design. One of the things I found out early on, after this golden age of making lots of polymers, was that if you had a highly crystalline plastic, it tended to be brittle. And so as a rule, most of what we deal with today is amorphous. Right? And so that helps it become much less sensitive to fracture stresses. Early polymers, if they crystallize, you would drop them on the floor and they would shatter. Right? So that was clearly a problem for plastics. But this consists of an irregular arrangement of chains, much like the spaghetti that I've been drawing. And so that is, as I said, it's the state of most plastics that you work with, that you come in contact with, is amorphous. However, there are plenty of instances where crystalline polymers are important to us. So milk jugs, 1 gallon milk jugs, they consist of about 1.2% crystallinity. So it's mostly amorphous, that polyethylene, high density polyethylene, all right, recycling number. Oh, come on, nobody uses the recycling number of milk jugs? What? 2. All right. Okay. Oh, that's also something you will learn by the end of the semester. You guys will learn these recycling numbers because you can go home to your refrigerator and see all these numbers right in front of you. Anyway, so the high-density polyethylene has a small amount of crystallinity in it because it improves the mechanical properties. And so when you drop that milk jug in the parking lot onto the asphalt, it doesn't explode. It usually bounces and doesn't break. They found that that small amount of crystallinity was very important. And so this consists of a repeating lattice, and so I've been drawing spaghetti. Polymers, when they crystallize, they can start out as something that's amorphous, but what happens is they start to line up with each other. And if enough of them line up with each other, then we have what's called a polymer crystal. All right, and so the dimensions of this are defined by the edge of that interface. So out here is amorphous, and in here is crystalline. All right, and unlike inorganics, you can never get to 100% crystallinity in plastics. Never ever. So if someone tells you that their plastic is 100% crystalline, you have to question their sanity. All right? It's not possible for polymers to do that. We'll talk more about that later. But this is the nature of crystallinity in polymers, and we'll spend more time talking about it later on in the semester. Cross-link materials, and so what Goodyear was doing is he had rubber, and he also had sulfur. Oops. And those sulfur atoms formed cross-links. And so they were cross-linking the short chain polymers and the rubber sap to each other. This is showing interchain bonding. You also had interchain bonding. And so the sulfur atoms, produce these chemical cross-links, and that keeps these chains from moving around. So that's why these rubbers stop melting in the summer heat. because those crosslinks were there, holding those chains next to each other and keeping them from moving relative to each other. And so this interchain motion is a very, very important part of polymers, and how we control that interchain motion determines what type of plastic we have, basically. A lot of things, a lot of plastics, almost all the plastics that you see consist of simple carbon-carbon bonds. So what's outside of those carbon-carbon bonds is what controls the behavior of those plastics in a lot of different ways. So these crosslinks, when they're there, can make these plastics very rigid, and they don't move very readily. And so the best example that you can go out and buy is 5-minute epoxy. All right, you have two components, you push them through the dual syringe, you mix them together and fix whatever it is you're fixing, but that mixing process brings two components into contact with each other and they form a three-dimensional matrix. It's totally bonded in all directions. All right, there aren't loose polymer chains that can move around in epoxy. They're all stuck together by these crosslinks. Okay, hopefully that makes sense. Oligomers, on the other hand, are very short chains, and so if we have something that looks like this, all right, and we have, in the case of polyethylene, all the hydrogens. You guys are very good at drawing these. Oligomers are considered short polymer chains, and a great example is underneath your shoes. The floor wax that was used to make the tiles in this room look pretty is polyethylene that's a low molecular weight. Not as low molecular weight as this. Oh, this part of my screen is still wet, I think. All right, and so this oligomer, and this is just an example. The degree of polymerization of this, which is the number of repeat units, is 5. We have 5 ethylene groups that made up that particular short chain oligomer. And so if you see that word, just think of a short chain, not necessarily a plastic. It is a polymer, but it's definitely not a plastic because it's too short to have the kind of mechanical properties that we need for plastics. And so that brings up another point, which is that molecular weight provides you with critical control over the state of the material. All right, it can't just be any old molecular weight. All right, polymer chains, polyethylene is a great example. We have short molecular weight polyethylene that sits on the floor. We have very high, ultra high molecular weight polyethylene that goes into hip implants, all right, or knee implants. You guys know of anybody who has one of those. They have ultra high molecular weight polyethylene in those implants, and that's an example of the gamut of molecular weight control and why we need that control to change the properties of these plastics. And then, as I've mentioned, we also have the backbone versus the side groups. And so, we can have carbon, and this carbon we think of as comprising the backbone of these polymers. All right, and so that's the core of a lot of plastics is carbon-carbon bonds. What we put on the outside of them, I've been drawing hydrogen over and over again. If we instead pull a chlorine in here and everything else remains hydrogen, what polymer is this? Oops. Skip ahead here. Got chlorine in it, which makes it PVC. All right. PVC has the same carbon-carbon backbone, but it has chlorine every couple of carbon atoms. PVC has a totally different set of properties than polyethylene. All right, so all the water you drink goes through PVC pipes, for example, unless you're in an old house. Then who knows what you're drinking. But hopefully not lead. Anyway, but PVC pipes are commonly used to transmit water everywhere now. And so we're not using polyethylene for that. PVC has the right properties for it. There's a higher modulus, greater chemical resistance, resists bugs eating it, things like that. And so this is an example of how you have a common backbone, but you change those side groups, and you completely change the properties of the plastic. All right, so whole industries come from swapping out these side groups. All right? So hopefully that makes sense. So we'll step through some examples of that later on. But you need to understand that there's a big difference And both contribute to the properties, both the backbone and the side groups. You can't just pick one and say this controls the properties. They both contribute to this. Make sure you keep that in mind. All right. And then we also have the process of polymerization. And there are two main reactions. The addition polymerization is mainly what we talked about so far. If we take ethylene and polymerize it, we're using an addition reaction. And that means nothing's left behind. We just have polymers. Condensation reactions are used for things like polyethylene terephthalate, which you guys will be very familiar with by the end of the semester. And this does have a reaction product associated with it. It has a condensate. All right. So these are the two main reaction pathways. Emulsion polymerization is what's used to make Teflon, by the way. That's what they need C8 and Gen X and so forth. There are a variety of ways, but these are the two main ways. And we think about two different types of structures usually. One is the homopolymer, which is what we've been talking about so far, where we have just the one repeat unit. We have, in the case of polyethylene, CH2 repeated endlessly. In the case of ultra-high molecular weight polyethylene hip implants, that's 1,000,000. In the case of Fluorox, it's 1,000. All right. Same CH2 repeat unit. Copolymers, it can go on and on. I just shorthand this so we have some type of chain group that is admixed with some other type of chain group. And this is why one of the reasons why there are so many polymers out there, is that you can mix A and B and get properties that are intermediate to A and B. So you can take polyethylene and make a copolymer with PVC and get properties that are in between the two. All right. So there's a huge variety of different polymers out there as a result of that. You can take PVC, you can add more chlorine into it. You get this high chlorinated PVC. So there's a bunch of things you can do. And there's a number of different rules that are used here. You can have a set variance, or you can have a random variance. And again, this can be used to control the property. All right. So very quickly here, thermoplastics. These are what we've been talking about. Individual chains which are not bonded together. All right, there are no chemical crosslinks here. I'm drawing them. They cross over each other. They can intertangle, which is important, as it turns out, but they're not chemically bonded except in that chain direction. They are separated by space, which is actually something called free volume, which is a very important factor that controls the behavior of these plastics, but they're not chemically bonded to each other. And you can have a neighboring chain that goes through and intertangles and so forth. It's also not chemically bonded to it. All right, they're just for most applications in plastics. Thermosets, on the other hand, worst case example is carbon bonded in many different directions. Oops, this is supposed to be carbon here. All right, so bonds as far as the eye can see. We think of these as thermostats. All right, and the example I already gave you was 5-minute epoxy, which doesn't look at all like this. All right, but graphite looks like that. You know, think of graphite as a thermostat if you want to. That's reasonable. And these, in fact, are only, one big molecule is one way of thinking about it, which is sometimes handy to think about. They're bonded. All the primary chemical bonds extend in all directions, so it's just one enormous molecule because there's no end to these polymer chains. There's little or no interchain motion, which is why 5-minute epoxy is useful. It's very rigid. All right, it's also very brittle. It can shatter easily, but in many cases we don't subject it to that stress, and so it works fine in that application. I know him. These have high strength, but they have low ductility. And as you guys should know already, there's a lot of yin and yang that goes on when we talk about plastics and in materials in general. You make high strength, great. You have low ductility, it means it doesn't shatter very easily. All right, there's a lot of give and take. Cannot be recycled. You can heat a thermoplastic up and reform the thermoplastic into something else. You heat a thermoset up, it just eventually catches on fire and burns. It can't be reformed into something else. Right, and then we also have what we started out with, which is elastomers, in which we have these polymer chains, And again, going back to Goodyear, we have a few sulfur bonds here and there. And so as you saw in my discussion, if you put a bunch of sulfur in there, you get ebonite, but if you put a small amount of sulfur in there, you get a few linkages. And the reason why rubber does what it does is those linkages are there, so if I stress the tire or it runs over a rock, the chains move past each other, and then those bonds, those sulfur bonds, pull them back. They snap them back into their original position, which is exactly what a rubber band does. All right, so those are the properties of rubber that we're familiar with. If we crank up the sulfur content, we get bowling balls, which don't make very good tires. All right, so a number of cross-links in the system have to be tightly controlled to get the right type of rubber properties. Okay, so there's plenty of consequences of this that make something useful out of something that is just a tree stack, for example. Okay, any questions? All right, so hopefully, see if this uploads in one continuous file. I'll see you guys on Friday.